those are fake cameras. That's fake.
All right.
Okay. So, actually, let's rephrase. So you guys have the option to work in groups of 2, or alone. If you guys, so if you guys kind of see, like, there's a bunch of test equipment. The one obvious one is probably the scope over here. There should be 4 per bench. So if you guys want to work in, like, kind of get yourself to a scope, you and your teammate, if you have a teammate, and yeah, make sure that's like. Why is this slug not plugged in? You can use it, but yeah, let's see. I'm gonna plug that in. Thank you. Awesome. Yeah, so let me go bring. Yeah. Yeah, and I guess meanwhile, just to be sure, since that one's not plugged in, just try to plug in your scope once and like see if it turns on. Just to be sure. Hello.
Fantastic.
Okay, yeah. If that's working, if something's not working, we'll figure it out. But yeah,
Alright.
everybody has a kit. Yes.
Raise your hand if you didn't get it. No? Alrighty. So, hello everybody. Welcome, and welcome to our lab equipment workshop. We'll do introductions in a little bit, but thank you all so much for coming. Thank you for staying till day on campus and braving the rain. And also thank you for finding this place. I know it's a little bit hard to find, so thank you guys so much for coming. First and foremost, if we can ask you guys to whip out your phones real quick and scan our attendance form. This allows us to make sure that workshops keeps going in the future, and also provides us a little bit of feedback for what you guys want to see next quarter as well. So feel free to fill that out real quick. We'll give you guys a few minutes. And while you guys are filling this out, we want to highlight our very special Dr. Briggs. Thank you so much for allowing us to host in this room, and for providing some insight as well. Antoine, is it recording?
Yes.
Fantastic. Okay. Everyone got that? Fantastic. So, who are we? Hello, everybody. My name's Josh.
I'm Sanjit.
And we're IEEE's workshops managers for 2023 to 2024. So, woo! So let's get right into it. A few of our learning goals for today are what type of lab equipment will be available in a typical lab space, getting hands-on experience with oscilloscopes, waveform generators, and plenty more. And we're going to be testing black box circuits to identify what they are. So in the little baggie you got, you have 2 little circuit boards that are wrapped up in tape. Don't unwrap them. We promise we'll keep it as a surprise for now. So promise you'll find out about those in a little bit. So let's get right into it.
All right. So why use test equipment? Well, you just want to test things. You want to kind of understand what your board is doing. Maybe try to reverse engineer what circuits are on it. If you want to calibrate something, it's just stuff you use daily life when you're hobbyists or working in a professional space for electronics. So so some common lab equipment that you'll find in the lab, soldering irons is kind of a must. Multimeters, waveform generators, scopes, power supplies. You have like other supplies, cables, scope probes, that kind of stuff. So more or less standard stuff. And sometimes we have even more advanced things, LCR meters, logic analyzers, spec A's, network analyzers, patchers. So LCR meters, if you guys understand the concept of impedance, it's kind of an impedance measure. You take your RLC network and you try to probe it, and then it'll tell you what the reactance and resistance of it is. If you don't understand what that means, don't worry about it. Yeah.
Logic
analyzers.
ED3.
Yeah, ED3, the Dr. Briggs. Logic analyzers is for digital logic, and for digital circuits. That's what you use to debug as your main test equipment. Spectrum analyzers, it's more for like radio frequency, solid communication stuff. You kind of try to measure what frequencies you're looking at to kind of test if that's working. Network analyzers, kind of similar to LCR meters, except for they tell you the output for all frequencies. Again, if this doesn't, or it kind of gives you a Bode plot. If you don't know what that means, don't worry. We'll even actually talk a little bit about Bode plots. PCB etchers, it's kind of if you wanted to DIY PCBs. Hello, do you want to pick up a kit?
In the front. Okay. Fantastic. So let's talk about our first lab equipment, a digital multimeter. So this is otherwise known as a DMM, one of the most common lab pieces of equipment, and very useful as well. So these are small handheld devices. I'm not going to read the whole slide, but the main things that it can measure are voltage, current, and resistance. Now, what you'll see is that on this little dial right here, you have a bunch of different settings that allow you to measure all these different things. So V for voltage, ohms for resistance, and amperage for current. Now, some multimeters can get pretty fancy, and you can measure a bunch of different ranges. We'll talk about that on the next slide. But a few nice bits to measure are capacitance, diode voltage, frequency for low frequencies, and plenty more. So let's talk about measuring current. Now, with measuring current on a multimeter, this is the easiest way to break a multimeter, so please don't break it. Pretty much you place one lead in the common terminal. Now, when I say leads, it's those red and black wires that often connect to the multimeter, and the terminals are these down here at the bottom. So the common terminal is the black one in the center. Now, depending on what you're measuring, such as current or voltage, you connect it to either of the two leads. So you'll see here at the bottom, it says A for amperage, that's when you're measuring current, and this one is for pretty much anything else, that's why it has all the other symbols on it. So you want to make sure that you keep in mind the limits when you're measuring these things. So when you're measuring a high amount of current, you want to use the left terminal, but when you're measuring, just this one.
It's not on this, but some multimeters actually, maybe check in the previous or next slide, because it might be there, but some multimeters, they come with MA, so you can kind of look at the symbols on a multimeter. It's always like somewhat self-explanatory. Over here it says A, and it's hard to read this, but it says 10 amps fused. So that means that if you're putting in 10 amps or less, it will be fine. If you put in more, it's probably going to break. There's some of them have this other additional lead that says MA for milliamp. If you measure anything over, if you're trying to measure 5 amps on that, you're going to break your multimeter. So just pay attention to signs.
Yeah. So
in EE3, you will never measure current. So you never use the terminal labeled A.
Yeah.
That's happened in the class. We've done that in the practically.
Yeah, you have to make sure you don't leave your cable in there, because that's a piece of it right into.
yeah. So basically, just make sure that you pay attention to which measurement you're trying to take, whether that be voltage or current, and make sure that you're measuring it properly. Like if you accidentally short circuit it, then it's the very quick way to blow a fuse. So moving right along to ranging. Now there are two types of ranging for manual and automatic ranging. This pretty much just determines like how fine-tuned your measurements are. Specifically, for example, resistance. If you're trying to measure 220 ohms, you don't set the dial all the way to like 2 mega ohms. Some of the multimeters like this one, it's a little bit hard to see, but it has like a 2 mega ohm, 20 kilo ohm, and like 2 kilo ohm. So you want to make sure that you're basically ranged in the proper area. Now, other multimeters that aren't as fancy, they just have automatic ranging. So it pretty much just whatever you measure, it'll automatically adjust. And normally it says, like it'll give you a measurement reading, and then along the top it has the symbols to it. So if it says like K ohms, then that means kilo ohms. If it says M ohms, that means mega ohms. Or capital M ohms means mega ohms. Fantastic.
Yeah, so power supplies. You might see some power supplies over on your station. Basically, a power supply is a power supply. It supplies power. You can set the voltage, you can set the current limits, and depending on interfacing with different power supplies is very different. Some of them have coarse and fine knobs, so you just adjust like the coarse, or you do coarse adjustment, which means like you'll increase a lot by turning the knob slightly, and the fine adjustment means that you just like tweak it barely a small amount. So like this is 3 amps. If I adjust the fine knob, it's going to be like 2.999, and you get the point. But yeah, they also have indicators. So there will be an indicator that says CV and one that says CC. CV means constant voltage. That means that it's delivering however much potential you set on your power supply, and constant current means same thing but for current. Usually when you get constant current, that means you probably shorted something or did something wrong, because it will be drawing a lot of current and won't be able to maintain the voltage that you set it to. But yeah, trying to see if that was something else. But yeah, more advanced features. Some get really fancy. This has so many buttons, but you can just you have a number pad for easy adjustment. You have multiple channels. Yeah, there's probably memory modes on this guy. Memory is kind of like it'll save what settings you have. Yeah, and some of your some power supplies, they come with a ground terminal, some don't. If you know what floating connections are, this is like a concern to you. If not, we have some slides on there. When we send this out, we'll have some slides, but they'll be kind of hidden. You can try to read about that or search it up online. But yeah, that's the power supply.
Yeah. So let's talk about oscilloscopes, what you guys have been waiting for. Now, these are one of the most powerful tools that you can ever use in the laboratory, because it measures all sorts of waveforms. So from the wiki, what an oscilloscope is basically a graphical display of voltage versus time. So that's it. But wait, there's more. So how do you actually use the oscilloscope? So let's jump right into it.
Yeah. So well, again, you're gonna need to connect your oscilloscope to your circuit somehow. So we use these things called scope probes. They have it's kind of a two-terminal device. There is a ground cable over here, alligator clip, and then there is the actual scope probe. You connect ground to ground, and you usually put the lead on whatever, or try to probe the lead on whatever device you're trying to probe. We're gonna just say for now, always when you have your ground alligator clip, always clip it to ground. Don't try to do any fancy things with this, because depending on what you do, you might be able to break your oscilloscope. So that's not fun. But yeah, it's kind of your reference point of the signal. So let's say you have some kind of fluctuating voltage on one pin. You have your alligator clip on ground, and then you take your scope probe, measure it on the fluctuating voltage, and it's going to show you what the waveform is. And that's kind of what you're doing with the scope.
Fantastic.
But yeah, scopes also come with multiple channels more often than not. You can kind of, your channels will look like this. So you're going to take your scope probe and you're going to put it in the BNC connector right there. And then, yeah, and we'll show you how to connect that in a bit. And then, yeah, sometimes you're going to be using some channels, sometimes all. These buttons over here, if you see them, these kind of turn on the display of the channel. So you can see right here, they're like all these different colors. Each color corresponds to a different channel. Yeah.
So the oscilloscopes that we're going to be using today, they're 2-channel oscilloscopes. So they're only going to have 2 different options. If you see on the one that you guys are using in front of you, you have like a 1 and a 2, either highlighted or not highlighted. Pretty much if you click the button, it'll either highlight or unhighlight. That pretty much just tells you if it's on, then it's going to display the signal. If it's off, it's not going to display the signal. So you can still connect an input to it and it'll read the input, but it won't display it on the oscilloscope. Fantastic. So here are a few of the display control knobs. So when you input a signal into the oscilloscope, you may have it set to a certain frequency, and once you change that frequency, it could throw off the whole display of the scope. So here are how you actually control how you display the signal. So it's pretty simple. You have vertical, horizontal, and position and scale. So this basically determines how much you stretch out the wave or compress it, as well as how stretched the amplitude is. If you guys took 102, it's like attenuating and oh shucks, I forgot the amplification and attenuation.
Yeah,
Yes,
you could say that it's more just like kind of think of it as like rescaling the units on your graph.
Yeah.
That's what it is.
And then moreover, you have different positions that you can set for the signal. So positions basically determine how offset you want it to be from different centers. So you could have it be offset from the 0 volt you can have it be offset from the 0 voltage axis. You could have it be offset in time to display different features of the graph. Now, the biggest thing for that is if you display multiple signals on one oscilloscope, rather than having them be overlaid, you can just change it around a little bit. And then finally, scales. These are the units per division. These tell you how much voltage and how much time there is per division on the oscilloscope. So if you guys will see, there are 10 lines across the graph. Each one of those lines is a division of voltage. Fantastic. So the moment you all have been waiting for, testing the equipment. So let's get to it. First and foremost, we're going to start testing our board. We're going to start with the big timer circuit. So if you guys all got that in your kits,
It's been really helpful recently.
Or lack thereof.
how about we Alrighty, everybody. So, in order to get your oscilloscopes and everything set up, we're going to need you to come up front and grab different supplies. So first and foremost, you guys need 1 or 2 cables.
There's a alligator and then there's a slug. There. Yeah, 1 of each.
So, you guys will need, you guys need a cable from Sanjay, and then clips from here, and then multimeters from Dr. Briggs. So, come on up.
I'm surprised how you mentioned that I can hear you from across here, and I'm sure this won't surprise you. I wish I could. Oh my. You're not helping.
Hey, you're getting double close right now.
Dude, that guy got so. Yeah.
Don't speak Arabic.
I don't speak Arabic. I don't do the filming. He knows enough. He knows enough to know what I'm saying. Yeah, you should call it.
I think only pairs. So if you're working with someone,
Yeah, one per.
one per pair, and then 1 set of alligator per pair.
Okay,
One for Zachary.
Okay, fair.
Sanjay.
Handshake, let's go, come on.
Okay, who else needs a BNC?
Should we use the CRT?
We have some.
Okay.
No spectrum analyzers. What? Really?
If you're on those,
You should be able to master all this, right?
if I'm on the, go ahead.
See how fast you can do it.
No.
I'm like,
Yeah, please do, okay? Then I'll have to hear you.
Okay, and everybody's also getting alligator clips with power supply.
Well, you said you did.
You attended my testing. What's the official stance on violence?
Let's take a seat if you have all your supplies.
Okay, David, you have all your supplies.
Fantastic. So, if you guys have all your supplies, feel free to grab a seat.
Wait, I don't have bananas.
Huh? Okay, yeah. This is just saying, yeah.
Everyone knows.
yeah, but I can, you should get like more of those things.
No,
So
don't.
you can actually horizontal it off. You
Okay,
need
so-
clips, yeah.
Everyone, just to check,
Oh.
you guys all have a BNC cable with alligator clips, a multimeter with also cables, and power supply also with cables, correct? Anybody missing anything?
Fantastic.
Some of the multimeters came with cables. If they didn't, you need to fix them.
I have one set.
Oh wait, we need one more set? Oh yeah, actually, yeah, we do.
Multimeter. Okay, yeah, absolutely.
Power user. Oh my gosh.
This is
Alrighty. So, can I get y'all's attention real quick? So, before we get too far into testing the board, we have a few notes for you. So, first and foremost, for test equipment, you need to have the enable/disable buttons for each channel. You gotta know when they're on or off. So, if it's highlighted, that means it's on. If it's not highlighted, that means it's off. So, for instance, Evans right here has a 1 highlighted and a 2 not highlighted. That means the 1 channel is on and the 2 channel is off. And secondly, in any electronics laboratory, you're going to find that red stands for positive and black stands for ground. Okay? So whenever you're making a connection to your circuit, try to stick by that convention. So black is ground and red is positive, or the supply voltage.
Another note, because some of your slopes have FFT on for some reason, diagonal, from the top right, diagonally like 2 blocks down, there should be a button called default setup. Everybody should just press that button. Yeah. And yeah, oh, another way for a power supply to kind of tell if your power supply is on,
Yeah, you
usually
don't have a
if
default
there's
setup on this stuff.
constant current or constant voltage is on, then that means that your power supply is on. Okay, and then I'm just going to use a mouse. Okay, so we have some power supply and multimeter tasks. These should be quick and dirty. We'll give you guys 5 minutes for this. Yeah, let's say 5 minutes, and then also be careful about current. If you're measuring current, be very careful. If you guys want to run it by me first, or Josh or Dr. Briggs, do that. But yeah, just make sure you don't blow out. And yeah, if things are not plugged in, then.
Wait, no, that's an AC. That's an AC.
And yeah, let us know if you have any questions or need help setting anything up.
No, that one's fixed. I mean, I can just use this one.
That's just this one right here.
Oh, well, that one's actually charged. Like, if you touch it, you can feel the capacitance.
Okay, so guys, sorry, one more note.
Listen up, folks, listen up.
Sorry, one more note. So we have a thing for measuring current. Let's skip that this time. If you guys want to practice that, we can do that at the lab. But yeah, let's skip that for now. Let's just focus on measuring voltage. Yeah. Sorry, let's get this through.
Oh yeah, you know the knob is on top of the thing.
Oh.
Plug it back in.
Oh, wait, I think it's broken. It's broken. Limit?
How do I set? Yeah, how do I use
We're not supposed to measure current.
Oh, okay. Okay. Yeah. So anyways, this is not recording. Anyways, so yeah, we'll try these set of tasks and we'll see like kind of the square wave with the really low duty cycle if you know what that means. But it should look something boxy. So yeah, go for it and yeah. Let's find out. Thank you.
How are you supposed to pronounce it?
Schubert.
Yeah, you need to get this like.
I'm seeing states No, God. I know what that means now.
Yeah, well, let's see. Go.
So I mean, you got this. Hey, look. So you kind of want to see the
Need a lot of steam. I didn't need
not like the horizontal.
like report.
Oh my gosh. Nice horizontal. I'm burning.
I go.
Okay. Also, guys, I say horizontal here. Sorry, I meant to put vertical. Try going for vertical first. Okay.
Oh, goodness.
Well, thankfully I did turn it off.
Yeah, well, you know what? Didn't you already?
Wait.
You said it's like, you have to go set it before plugging it in.
Oh shit.
That's cool.
I very likely Steve.
It'd be cool if we could use a funny, like, animal.
This is if you're doing it.
Yeah, you wanna know a magic trick? I wanna know a magic trick. Don't trust this one. Don't do anything.
For the auto
The
scale?
only people who
Okay, but out
Your special release. No, it's good. It's good. That's somebody out of the telling him he went to the golf club over the weekend, and I told my roommate to ask him, hey, you guys remember this can be very
And if
happy.
it goes first, don't touch this.
you guys have basically did make like the other part of the rest.
Yeah. Yeah, we made them like, we were the first group to finish and how we the next day we came to
Because my thing was good, just that I was designed slightly wrong.
And Cameron did it wrong.
These like little like
Yeah. In your
I
situation,
did it correctly even though my capacity was like
scope probes are usually like have a 50 ohm pressure on them, and this one does not. These scope probes do not. They're just PNT connectors. That is my guess.
Just did what you did before. No, like now you're connecting the mine that has to go to ground. I know that's what it
Is there a way I could
They're sorting ahead. Why can't they just like use an actual probes? I don't know. And just like connect this to like this guy or something so it doesn't ran up around. So should I put this? Yeah, put some
this is to the out.
Yeah.
This is to the in. I mean, they're short anyway.
Plus, you didn't even plug it in. They were voltage.
Yeah, I know. I know what you're
What? Yeah, so I told my goodness.
You're gonna accidentally make it for 30.
It's my turn to go. So
Yeah, it doesn't matter if it's on
sorry, I didn't use it. No one saw the or something.
This is the kind of thing that this points out why it's so because people care about this stuff right now.
I mean, usually they put it in.
They don't want to see that.
Yeah, did you know that if you press the auto scale button, it'll automatically do everything over you? Wow, magic, so cool.
You're jumping ahead. Two.
Auto scale one.
Don't jump the guy.
Right now you won't be able to get anything. You know what to check?
actually.
I've heard of it before, but I don't remember.
It's a filter.
We rapped
My
about it.
video and trigger.
Yeah.
I don't remember that. We've been around. Wait, was that the one we were building? Like the one we did on spot?
No, we're not sure.
Okay, well then do your best, okay?
Take a look at why is yours different? See, yours is different than yours. Tell me why. Tell me, how is it different?
You mean the height of the peak?
See what's different about those two systems, about those two displays. What's different? No. Come on. Look at it. It's slanted. That one's not.
So why are you here? Why are you me? Yeah. Yeah, I like something.
Alright.
It is like
Alright, everybody. We're gonna keep going with the workshop and on to our next activity.
Yeah.
So,
Oh yeah. Let's see what's next. Okay. Yeah. So.
a little bit, first off, on signal capturing and triggering. So, you guys may be wondering, or you might have experienced this, why your wave gen doesn't look like that, or why your waveform doesn't look like that. This pretty much just is the amount of trigger level that you have. So what the trigger basically does is you set it to a certain value, say for instance 3 volts, and then if your wave ever crosses that threshold, that's when it's going to start reading it. So, for instance, these timer circuits, they're operating on 9 volts. So if you go anything above 9 volts, it may not actually trigger. So then your waveform will actually look like this, where it'll just be jittering back and forth. Now, technically, if you guys want to, you can do this. It's called a roll mode. I actually didn't know about that. That's Sandra's doing. So if you guys want to make your waveform look like this, feel free to just ask them after the workshop. Okay.
He's the same. Okay, it doesn't.
Okay, yeah. So, kind of on the topic of signal capture and triggering, when we release the slides, you guys can kind of look at how analog systems work. It kind of gives you a little more insight into this stuff. But basically, yeah, like Josh had said, what's happening on your wave, on your scope is every time it crosses a certain threshold or meets a certain requirement, it triggers. And then it's going to start displaying from that point on. So, kind of the way this works is every single time it triggers, it will start displaying your waveform, and then it will do that again and again and again. So that's how you kind of get the consistent, nice looking waveform that you have. There are lots of different triggers, and let's see. Oh yeah, so this is kind of also more a little on what it actually does in the trigger process. It just kind of collects your waveform, puts it on the screen, does it again and again. There are like different types of triggers. You have your rising edge, falling edge. So if you guys kind of look at the signal you have, it rises and then it falls. So that's a rising edge and that's a falling edge. You can set triggers to that. You can set triggers to slopes. So if the rise over run is really high, that's like a slope trigger. You can have pulse width triggers. Yeah, there are lots of different triggers. There should be a trigger button on your scope, so if you look for that, press that, you might be able to see what kind of trigger types you have. Yeah. So.
Fantastic. So a little bit more on some of the more common advanced features. Measurements. So these measurement buttons you guys see on the oscilloscope that we have, a little measurement button.
Real quick.
Right here. So it should be labeled about here, the measure button.
Alexa.
Okay. It should have cursors and MEAS. That stands for measurement. Now, what you can do with this is you can measure different signal, different parts of the wave. So you can measure the peak amplitude, the min-max amplitude, the mean cycle, everything like that. Like with frequency, what frequency you're operating at, and things like that. If you need to head out, no worries. Just, you need your memory card? Okay. Can you take it from here?
Yes.
To the slide.
Yeah, okay, yeah, and then you also have your math functions. Again, like Treasure, there should be a button called math. Math does a bunch of cool stuff. If you have multiple signals, you can kind of add them. You can do like all addition, subtraction, multiplication, blah blah blah. You can also do mathematical operations on a single channel or a single waveform. You can do like FFT, if you know what that is. Derivative, integral, square root, that kind of stuff. Yeah. And yeah, some scopes have even more advanced stuff. You have reference waveform triggers. You can have just reference waveforms this way. Digital logic analysis. It's kind of like a logic analyzer on the scope. Data logging. You can take a thumb drive, put it on there, see what collect information. Sometimes you can directly connect these to USB to your computer, and you have history, so you can kind of acquire, store, and then look back at it. My scope has a Bodhi plot. This is a more rare feature, but it's really fun. Bodhi plot, if you know what that is, it just tells you all the frequency response. And yeah. Oh yeah. Also, we did not really tell you this at the beginning because we wanted you guys to struggle and suffer. But there's this magic button. It's called Auto Setup. Go ahead and press it. See what wonders it will take you.
Auto setup should be this button right here, next to the signal run.
All right.
So just a fair quick note on auto setup. Pretty much it just basically automatically sets up the wave to make it sure it's the proper scope inside your view frame. However, it might not accurately read like all features of the wave, especially when you go to more advanced waveforms. So take it with a grain of salt. It might not give you like the exact thing right away. So you still need to practice these moments of going through the horizontal scaling, vertical scaling to make sure it fact check the auto setup.
All right. Cool. So now CAPS set 2. We're just gonna try out the math and measurement buttons. Try to measure the peak-to-peak voltage of your signal. So, like basically with the low point and with the high point, peak-to-peak is the difference of the high minus low. Frequency is frequency. Your scope should be able to tell you that. So yeah, go click on the measure button. Go up.
Yeah.
What is this?
So this is.
And if you guys get ahead, try taking the
This scope is
F15.
really, really cool. It's gonna be.
The flyer?
Oh, of course. So now there's nothing, so, yeah, anyway, the measurement. Okay, it's already good, it's already good. See, it says 16, and it's giving you pictures to show you where the last.
So there's something that signals when
You want
right? Now over here you have this waveform. How do you know? Like it looks very nice right now, right? But there has to be some way for us to synchronize it such that every single time it shows up in the same spot, right? So that's where the trigger comes in. In fact, if we get rid of it, you know, it is like the orange bar is the trigger. Right now it's touching part of the signal, so every single time that it sees the signal, it knows, I'm at that point, okay, we're going to start drawing pretty much like on top of each other. If it's not on top of anything, there's no synchronization between any of the signal and you end up with a load of garbage. I mean, like, yeah. Now here's the problem. You see how you have these three lines right here, which no one else seems to have, okay? So if we're triggering on something which is overlapping multiple times, what you're going to notice is that there's still now some swimming going around because there's three things that it can possibly trigger. So when you trigger it, you generally want to move it up such that it can only trigger on all lanes. And now it's going to, okay, maybe I went too high up. But now it will only ever trigger on one thing. It still has a little bit of like gobbledygook nonsense going on. But I have a feeling that that's due to the fact that the frequency is changing, not the one. And yeah.
No, it's not
Sorry, what's your name? Larry. Okay. Oh, I'm Alexi. Yeah. Yeah, but I have a feeling that when you're touching this, what ends up happening is that you're changing the capacitance. And the frequency at which 555 operates depends on the capacitance. Because we can like put our finger above the space here. And obviously there's nothing soldered to the trace, it's just a wire. And what you can notice is that our signal's frequency ends up changing. Something funny going on there.
I mean, you can see the harmonics though. And you can see those are the resonances of the harmonics.
Say to measure peak to peak. What it's going to measure is
Oh,
not
God.
from here to here. It's going to measure up to that point right there. So if you hit the measure button right there, and then you can
Alexia, have you heard of the power of French?
peak to peak, and you can see these crystals are telling you
Do you want to show
where
them
the
the power of French?
peaks are.
Okay,
And
wait.
that's how we do it.
I'll just.
It's a different kind
No.
of
We
measurement.
don't want to do that.
And you can actually see the curlicue is here.
You never do this. This.
And you
Wait,
can
you can zoom in a bit.
and here's peak to peak, which you can measure minimum, maximum, and
Wait, where's the
Not by this, I think so. Okay, wait, actually you ran
Okay, you
into
did.
a pile of
Wait,
fish.
stop.
So that's some of the really
Stop.
tricky
Touch.
things you can do with these
Okay,
digital scopes.
so they're an FFT, you're gonna trade
You can't do this kind of thing.
time for frequency. So right now you can see the signal here all the time. Now what you're going to want to do is you're going to want to zoom out quite a bit.
So, yeah,
And when you
it's
zoom out quite a
smart
bit,
enough to
what
say,
you're going to
well,
notice
okay,
is that all of a sudden your frequency is going to be shrinking. So you're zooming out in one, you're zooming in and
that's
out.
we're going to take back.
Oh, it's actually
That's the
okay, there we
if you take
go.
a
So
look
now
at
we can see the
figure
first few harmonics
that they are
of the
showing
signal as
here.
they go.
Wait.
Say, okay,
Then let's actually zoom out a little bit more. There we go. Now I think it's much clearer to see where the
that's
actual
the way
peaks
the
are.
algorithm is.
So if you zoom in for just like this much, you're not going to be able to get much useful frequency information about the signal because you just don't see enough of the signal to be able to tell which frequencies are present.
This is meant to just
Part of the problem is also the fact that it's using an FFT to compute this. So an FFT needs quite a few samples in time in order to give you detailed information about the signal and the frequency. Now you're zoomed too far out and you're just trolling.
Yeah, I'm trolling, I'm Alexi.
Oh, that's why.
Yeah, you're going to see it next year? I mean, next quarter?
Yeah.
Oh, kidding? Yeah.
You're not.
Bro, it's like our team is made our first year. And a team-year transfer.
We're the first one done. Hello.
And not
Do you want to say this? Yeah. Do you want to see the power of friendship?
Outside of my friendship?
Yes. You touch this? If you touch this, it changes.
Yeah, I think maybe if you touch it.
Both of these should set off.
No, you're probably holding on to it too much.
Okay, so the FFT just gives you information about like the signal and the frequency. So sometimes you want to know which frequencies are present in the signal, and the FFT is able to do that. That being said, FFT is kind of annoying. You can't tell anything. Well, not pure noise. It actually does have some information you want. But you're going to be trading time for frequency information. So if we look at it like this, right, the sun will actually start seeing peaks, right? The more we zoom out in time, the more we zoom in frequency. So now we can actually see the peaks corresponding to all of it. This is particularly useful if, let's say, you're designing I don't know, radio transmitter. You want to transmit at a single frequency.
so
You could use
what that is. So if you
probably not FFT, but a spectrum analyzer better thing to be able to figure out which
It's 20 kilohertz.
and to make sure that the CC doesn't get mad at you because you're transmitting
this
online.
says 10 to 1. This says 10 to 1. On the scope probe, you have these attenuators.
Yeah, trigger a nuclear missile or something.
So 10 to 1 means it's switched by hand.
I can't believe I'm going to say this, but
You missed this? Dude, of course you do. Are you kidding me? Dude, you went to 8 a.m. section. You don't even know how much you were missing at 8 a.m. By your section, I was already tuckered out, okay?
Bro, wait, no, wait, you were energized? You were more energized than any other.
Dude, you kidding me? I was holding 7 a.m. office hours. Of course, I was really
See, he hates us. He didn't want us to show up.
No, dude, you guys are like, oh, we want an extra office hour. So like, instead of at 8, they start at 7. Okay.
Yeah,
No one
no one ever showed up. Did anyone ever show up?
Yeah, dude, I have a photo. There were over 20 people who showed up before 8 a.m. one time.
What? Was it like the day?
I'll show up at 7 and just ask you down.
They're just bringing it down. David, you already do that.
Just doing math is not gonna like.
Oh my
gosh.
David, take a seat, okay, or I'll smite you.
Whoa. This is threat of violence?
This is what?
Is this a threat of violence?
Fast food trends.
This is not a threat of violence. This is a perfectly reasonable response to being annoyed.
A different, more serious question. If I actually wanted to measure that,
I'm glad you asked. Okay, so actually, okay, we're doing a dual demo. Okay, which let's swap seats, you and I. Okay.
You know he always wants to.
he's gone to PCA.
Okay, so what you do is you click the measure button, or you can click the cursor button. I personally prefer using cursors. Now over here you can select the source, either channel 1 or map. And now what you can do is you have your measure thingy here, you click it, says click to select. And what we can do now is we can move the cursor to one of these. So it looks like this frequency was 16.9 kilohertz. We click the second one, and now we're moving the second cursor over, and what we can see is that it's at 33.8 kilohertz. Okay? So this one is twice that one, this one is 3 times that one, this one is 4 times that one, 5 times that one. Now, in theory, you shouldn't see this. For a square wave, you only have the odd harmonics, not the even ones. Which I have a feeling the only reason we're seeing them is because someone. No, we still see them. But this is also isn't a very good square wave. If you notice it. Yeah, they're trapped. It's not even a Gibbs phenomenon. The problem is that it doesn't have a flat top. So okay, now that we have a flat top on our wave, let's zoom out. Yeah, we still have it. We also have a whole bunch of other garbage here because it's not a particularly good square wave.
I don't know what computers will look like. So
The what? Yes, I know. You guys have told me that about 50 different times.
oh yeah.
What, we have to add these ourselves? What do I look like? Do I look like a peasant here now?
Math.
Dude, you really, dude, don't say that.
See, this guy is cool.
Yeah.
That's why that's why they left.
UCLA just like, I'm gonna report.
Yeah,
I'm gonna talk to human resources.
You're gonna talk human resources.
Alrighty, everybody.
Yeah, I'm gonna get Alexia.
David, let's take a seat real quick. Fantastic. So, let's keep it going to our next activity, waveform generators. So, these are the third and final instrument that we're going to be using today. If you guys haven't seen them yet, this is a waveform generator. Ooh, ah. Okay, so how we use the or a little bit more about the waveform generator. They can generate all different types of waveforms. I'm not going to read all the types out because then we'll be here forever. But you can basically adjust the different parameters of each of these waveforms. So you can set the frequency, the amplitude, and an offset, for instance. Like if you want to oscillate between 0 volts and 1 volt, you can set the amplitude to 0.5 and then set the offset to also 0.5. It'll oscillate between those two values. You can also create arbitrary waveforms, but in order to do that, you have to basically search up the software for it. It's a little bit difficult, but like you can do some pretty fancy drawings with the waveform generator. So it's a cool piece of technology. We're just going to dip our toes into it today and get you guys a little bit more qualified. So a little bit more on this. Some of the more advanced waveform features include modulation. If you guys took 102 last quarter, we talked a little bit about modulations and communication systems. So the waveform generator can actually do modulation. You can also sweep. So the sweep is what we're going to be using in a little bit, but that basically sweeps from one frequency all the way up to a very high frequency. So you can go from instance from 100 hertz to 100,000 hertz, and that basically outputs anything in between. And then what we can do with that is we can basically interpret that and test it on our oscilloscopes. Finally, you can do channel coupling. This basically allows you to copy your one set waveform to the other one. Say you have a really complex waveform and then you don't want to have to retype all the parameters into the waveform generator. You can simply just copy it right over. Fantastic. So we're going to be focusing on the final bits of our boards, but we're going to start off with this Chevy Chev filter. So that's the elongated board at the bottom, and let's get right into the task.
Okay, yeah. So kind of for precast, this is what precast is. Let's see. I think it might be nice to share slides.
Yes.
Because we have like kind of outputs what you guys should be expecting. So I forgot what the tiny URL for that is. Okay, so yeah, and the BNCs.
Okay. So for this task, you guys are going to need to connect the waveform generator to the second channel, the oscilloscope. So I'm going to be passing around these cables. These allow you to connect directly between the two. So.
Oh,
Oh, I see.
What? I'm David. Oh, you're David's replacement. Nah, you're not David's replacement. You're
okay, yeah, actually,
Alright.
you can kind of look at it over here. If you did it right, it looks something like this. But, back to
Oh my god.
Or okay, this guy can back me up like that one guy like has the wildest.
Oh,
and then David's like, hey, Alexi, that's kind of funny. And I'm like,
You're not supposed to say that.
I remember that was funny. I was in the back.
you're in the back. Yeah, you were like the least likely to get shot.
Yeah, exactly. I ran in there. I was like, I gotta use the bathroom. Went in there for like 20 minutes. And then right when you stopped, I was like, what did I miss?
Rice is and what did you miss? You missed the like you missed the fun. Oh my god, dude, David's like,
Okay, so should
Bro, you know, I kind of want to go to church now.
dude, you go to church?
Oh, did you?
Yeah.
Oh.
Actually, I went there in Lebanon once. Like this winter. Before that, it's been like a year or two.
Tell me what Tyler Price is visiting on the 9th.
Who's Tyler Price? Oh, Tyler Price. Yeah,
Wait.
Micro Mouse Lead.
This is the rap guy. Yeah.
We gave him the chance to the suit,
You know
right?
Tyler Price.
I just know Lakin Ball.
No, you don't.
What's the power?
You know who that is.
Chance to the suit, yes.
Yes.
Oh, you don't? Okay, never mind. Then don't show up.
What church is it?
Don't worry about it.
So basically on Sundays, which church?
Okay, dude, I'll message you. I'll message you.
Yeah,
Okay, don't worry.
you know the upside down coffee?
Upside
Do
down.
you know upside down coffee? Right next to joint. Jews for Jesus underneath.
Yeah, that's all.
Yeah.
Hey, dude, this is Mallory.
You need another.
Omar is my friend who's probably in Saudi Arabia.
Yeah.
The Commons LA and stuff. It's underneath.
Yeah, just search
Jews for
on
Jesus.
Just search on the phone.
What a coffee joint. Upside down coffee. Go there on Sundays.
Okay,
10
so
in
if you look on the
morning.
board, it should be kind of labeled. That's the filter. This is your
It's
filter.
okay, you know what? You can sit next to
Oh,
David.
I get it now.
I'll put these waveform generators and stuff.
Yeah.
And scopes.
Wait. Be careful. That's channel 2.
What?
That's
Yeah,
channel
also,
2.
guys, make sure your channel, you have the BNC connector in the right channel, and also make sure your channel output is turned on, because otherwise it's not going to.
Okay.
Yeah, if you, oh yeah, that's fine.
I'm out of here. I'm damaged now.
Catch you later, Lexi. Thank you for coming.
Yeah. Sorry, I don't have any adapters.
No, that's right. But you need something to go into the filter. The filter support.
So, channel
Yeah, so we use the same scope.
Well,
So
since
you
this
get an extra piece.
Yeah, I don't need those.
Okay. Yeah. Here are weights passing along. You get your alligators.
So you plug in out or in ground?
In ground. And out you connect it to the both.
Okay. Also pass these along.
So channel one. Wait, alligators. Oh, alligators.
So you get an extra beans.
Both of your channel one should be used as the out there, but
So channel one on the
that
way
and that.
the input then.
and then pretty much we just connect channel.
BNC filter. You have an extra BNC?
You do need one, please.
Alright, so
No, I think you might just have it.
so let's
How many VPPs are we doing?
channel 2 looks to be
Yeah, so also, if you guys look at your waveform generator, kind of towards the bottom center, there should be a button that says channel 1, channel 2. Sometimes you might have to press that. If you press that, you switch what parameter you're changing, kind of.
so what we're going to do is we're going to get the next process the wave generator and then we're going to observe it on the so separate all the cables.
Channel one on the out, channel two should be the.
I will take that class just to bother Alex.
Huh?
I will take that class just to bother Alex.
I mean, you kind of have to. I think you
That's
need to change
what's
that for a while.
Thunder. To be clear,
So out on the ground.
channel one on the wave
And
generator.
then in and
It
ground.
goes to the input on the filter.
Yes.
Channel two goes to channel two.
Yes.
Channel one here goes to the home. And then.
But you have to also connect ground correctly, right? Ground to ground. Both the waveform jet, like you have ground connected to output. So you want to connect the red one there instead, and then ground.
Gotcha. That's what it's about. Whoa, whoa.
Look at that! Okay, so one of your things is, so both of your channels are not at the same frequency, so change one.
Wait. How do you change that?
Well, you see how like this is, yeah, so there should be like the channel 1, channel 2 button down there.
Oh.
Yeah.
Oh, this is at 1.5. Wait, how do you move it to the?
Oh, there's a left, right button,
I don't know what's happening.
like right below your knob. Yeah.
So
There you go.
what we're basically asking you to do is, so we're observing channel 1 and then
Wait.
yes.
Oh, because this is
This is just
There you go.
so this
Also,
is
it might help for some of you guys to turn off your
so
FFTs.
observe
It might help to turn off the thing.
The computationally.
Wait. Mine's
So that right now you just see these. So your ground is connected.
okay. Bottom one is
Yeah. On the upper.
So there on here there's a button that's called channel 1, channel 2. Press that and then
Oh.
set that to 1.5 and set
Oh, it looks good.
What did I do?
Press the auto.
Huh?
Press the auto scan.
Yeah, that's what I did.
Yeah.
Oh, just set it at 1 kilohertz.
I don't think you're maybe. Oh, because you don't have both outputs.
Oh yeah, this is
Yeah,
how
that
it
was it.
looks.
It looks.
I just grabbed the cable.
This makes much more sense.
Oh, you need to connect
So confused.
channel 2.
Mine is
Oh.
Mine is
Cool, awesome. Yeah, you have a face.
Why is it so delicious?
What if you could do multiple
See what the images.
I don't get why we should be plugging those. Wait, Sanj,
Yeah.
do you know why we're plugging those two together?
Kind of
You're all good?
see what the original signal is.
Oh, okay.
Both to see
You're all
one,
good?
have one show the original signal.
Yeah, so you turn it on and then
Yeah.
put the live thing. Oh.
So yeah, that just means that.
Okay, just adjust your channel 2 to match your channel 1.
For the most part.
So this is set to sine of 1 kilohertz. So just make sure this is set to sine of 1 kilohertz. And then you should be all good.
Okay, also one thing, if you guys press auto setup here, it's gonna kind of offset your channels. So if you look at your channel scroll buttons, below the number which is glowing up, like where it says number 1, number 2, and it's glowing, below that there's a knob. Just press that knob. It's gonna zero everything, and then that should be like awesome.
Yo, whoa. Now it's on top of each other.
Oh yeah, you just change. Okay, so if you're doing it based off of one channel, it's not the other. Right now,
What if we generate
you guys have
square
frequencies going, then it's
Whoa.
kind of sus.
Strange.
You also
Wait, that's so funny. Yeah.
I swear it didn't explode.
Close?
Oh, if you just press the knobs. These two knobs.
Sanjay,
That zeros your
Sanjay, this is so funny. Look at this square.
that's
It's
what I-
all
Yep.
all wiggly.
Yes, that is what. Yeah.
See, but yours
So that's
is
the
more
filter,
stabilized.
right? Because it acts like a
nice.
filter. It'll filter out the high frequencies, keep just the low frequencies.
Wait, is there, so there's a high pass and low pass filter?
That is the Chevy Chev. The Chevy Chev is a low pass, and then red and black one is.
Okay, you're all good.
We'll figure out.
I'm good with the. I think it was that function generator. And my extra credits for EC3. I had to change.
Look at my beautiful
This is where it usually used to sit. I changed my forces.
We gotta use that one.
Huh?
We gotta use the big old one.
No, that's just no so stuff.
Yeah.
No, but it's that function generator.
I can produce noise.
Jonah, are you all good in the back?
Wait, the noise.
Stuff always breaking.
Yeah.
That's great. What is R?
R.
I did not.
I think mine is almost.
What it sounds like.
Is it just like random?
Yeah, it just. Oh, R. R is RB2.
Yeah, I'm just looking at what is
That is kind of arbitrary, but well, arbitrary is a set, so you use your computer
The
software.
thing is, it's just gonna show up to his office hours, like not even that.
Oh, yeah.
It's just a sound.
They're on Discord, by the way.
The office hours?
Yeah.
Yeah.
It's good to get back our
Well, get back your ID card. That's kind of important.
I bet people use their master.
You might not be able to get
Is there
Are you like
voice
when? It's 22.
So just kind of.
Wait, but is he doing the master's PhD thing together?
He did his master's with BS.
Oh, so he's
Yeah,
having
like
a.
these
David's
yeah, like these are so short.
And
Okay.
So I'll just doing it slightly different. Graduating
Oh my God.
in 3
I'm a materials engineer.
that's slightly crazy.
They did a whole
He drives me on to like every event.
Yeah, so they're going to
Also,
graduate.
other guys with a physics tech grad too.
Yes, that was fun. Let's go.
He's graduating.
Wow.
I'm also gonna graduate. But I'm full transfer. So
I think I might be able to graduate in 3 years.
yeah, you don't have a he just
Yeah,
he's too lazy.
I'm too busy looking up pictures of his sister.
He's like, I could just take some classes.
Seriously? No, I have to take the full.
Yeah, I think that's your graduate.
But then I can do the same thing that Zaire is doing.
Yeah.
So I
Or
might.
you can do MSBS.
Yeah, well, I think he essentially doing MSPS at the same time.
Apparently, we
Because
can
it's gonna be done like
floor.
halfway
They
covered
said
in
like, yo, the proof is bigger.
Yeah, but
I mean, also,
so you won't be able to retake the master's.
Yeah, they have like actually like huge.
and like we should actually like just like
Like the only confusion here is
The master's
you still have to
yeah.
take a bunch of master's shots once you're
Really? That's stupid.
Yeah, so
That's it,
Alexi's
that's
done
it, literally
Alexi's
something.
done there. I shouldn't take practical classes.
So this board is a Chevy shirt.
And they'll count towards the
What we'll see.
But it would be
But this is just like.
But it's only, you have to take 8 classes, right? The master's program? That's not that much.
Yeah, but then look at the first one. We're almost home like machine learning.
Go to Massachusetts. See if they accept.
I will go to Massachusetts.
Massachusetts? Master?
Oh, the guy who just called.
oh no, we actually did it.
He can pronounce
Alright, so moving on, because we still have a little bit more to go through today. Let's see, why is this not working? Morning. Okay, yeah, so you should probably have something that looks like that, minus the fancy colors, because Keysign is not fancy, JK. And let's see. Okay, so why is this? Okay, so we're gonna try playing a little bit with the waveform generator right here. So like I mentioned before, the board you have right now is a Chebyshev low pass filter. What that means is if you give it an input signal, it's gonna try to diminish the high frequencies and keep or let the low frequencies pass. So let's try adjusting it. You don't need to worry about both channels or channel coupling. Let's just focus on one channel. Turn off channel 2. Focus on channel 1 and adjust the frequency, going from 1 kilohertz to 10 kilohertz, incrementing it like 500 hertz at a time. So there should be like 2 noticeable things. One where the frequency starts to drop a lot because it's a low pass filter. You're increasing the frequency of the signal. At some point, it's gonna stop. The signal's gonna stop coming through. And then there's one point where the signal should basically completely vanish. So just try to note those 2 points, and then tell us what frequencies those should be.
Yeah. So just a little bit more of a clarification. So on your waveform generator, you guys see a knob on this side. This is a different model, but this knob helps you adjust the frequency. For your guys' models, there'll be 2 arrow keys underneath. That basically adjusts like which place you want to edit. So if you go to like the 100th place after the 1 kilohertz, you can adjust it manually with the knob, and then that'll basically tell you like, or you'll basically be able to observe what frequency.
If that's not changing, that means you're set to channel. Oh yeah, you're set to channel. Okay, you're good. Adjust between like 1 kilohertz and 10 kilohertz. Yes, try to stay between 1 and 10 kilohertz, guys. Incrementing it faster. Okay, yeah, so we're incrementing at 500 hertz at a time. So right now you're at 1 kilohertz. Go to 1.5 kilohertz, 2 kilohertz, 2.5. If it doesn't change. So if it doesn't change, then you're probably outputting the wrong channel. So if it doesn't change and your channels are like turned off, press the channel 1, channel 2 button, because you're probably adjusting the parameters for channel 2.
So what we're gonna do is
I keep forgetting channel 1 is under channel 2.
Yeah, I know, it's so frustrating.
That's a problem. You can also just use a knob if that might be faster. You just twist it. You don't have to okay, so you see it's highlighting 1, right? So if you do this,
Oh.
Wait, did we do Chebyshev on that? I thought it was just or C filters.
so press
Oh,
yeah,
this is
sorry.
right.
So gonna be the test of this one, which is
It's so
doing
tiny.
so change it to yeah.
Okay. Oh yeah, it's dropped down. Ooh, now it's basically gone at 13. 12. 13 is just the
This is
Oh, my knob is just bad. Okay, good. I was going to say, because like,
yeah, now it's increased.
yeah, you can decrease it. There's
yeah.
like,
You get
there's like
Yeah, it
a,
starts to.
there's like a tiny range where you can decrease. After that, you are not permitted to decrease this. It just doesn't work. It's so weird.
That's great.
Josh default online.
Huh?
Josh default. Mine doesn't kind of doesn't work.
The
I think the function. I have my extra credits on this one.
Yeah.
It's fun. I think this is fun to do. So I'll change it for you. Nice. Oh, did you get channel coverage to work?
Let's check.
No. But yeah, like the frequency is
Oh, I keep
going
forgetting
with the journal one.
Why?
I keep forgetting that. It might be noise. No, wait, no. Your channel's off. That's just weird. I don't know why it's doing
That's suspicious. I don't understand anyway.
So, what frequency do you start seeing a noticeable drop at? You had like 10 kilohertz. Yeah, it's dead now.
It's like,
Is it one? I think it's the Chevy can you lend me your Chevy Shark? Let's just like plug my power.
What about you? What frequency do you think you're getting a massive drop at? 964. We can go.
Oh wait, you need to run it.
No, it is running.
No.
My head, it's running. It's fine.
So I do suspect. Wait. So if I change it here, does it change?
oh, right, I forgot about that.
Oh, yeah, it's changing.
Repeat this with the square and the triangle one. Right?
So it might be my Chevy Shark.
Where was that?
Or you're also.
I think it was
Well, no, it
supposed to
was
be
working fine before, yeah, then it's under your filter.
Does it look like a square?
Your LPF.
A square.
It's supposed to be a square way.
You mean like
That's
this is like
subjective.
incomprehensible?
I find it like
So-
at 7 kilohertz.
So remember that. Okay, fantastic. So let's go down to the 100th place and keep going lower. So what do we notice about this wave?
Oh, it's like it has a trigger or like the spike.
Ringing.
Yeah,
The ring, yeah. So if we keep increasing the frequency, what's happening? To go back down. We'll notice that it keeps getting filtered out, right?
That's not even that's the
Until
static.
it becomes sideways. Does that make sense?
Wait,
So we'll basically just think about why is this happening? So if we consider that this is a low pass filter, if we keep increasing the base frequency that we're operating at, how is that going to change how the filter reacts?
So low pass filter filters out
All the high frequency signals. Yes. So if you don't have a low enough frequency to form the sine wave, to form the square wave, you're just going to end up with a sine wave, right? Does that make sense?
You can try using.
So if we think a little bit about how a square wave is composed, we can decrease this
Okay.
back to its value. You ready to go? Okay. I'll come back.
Well, I'm just first with this.
Triangle wave. Is a ramp wave a triangle wave, Richard?
Oh yes.
Yeah.
I-
Yes. Okay.
Okay, so we're gonna move on. If you guys didn't try this with square and triangle wave, that's fine. Feel free to come by IEEE and do this again. Okay, so we're gonna talk a little bit about Bodie plots and frequency response. So we're kind of like very hand wavy with how we're measuring the output over here, or like how we're being like, oh, it's dropping in around like 3.7 kilohertz or 4 kilohertz, something like that. That's like around where you should see the drop. But we're going to talk a little bit about what a Bodie plot is. So basically what a Bodie plot is it measures your frequency and phase response. So when you have a filter or a linear system like the one we gave you, what it's going to do, it's going to take your signal, it's going to do something, it's going to do something to the amplitude of your signal, and it's also going to shift your signal. So if you guys notice, some of your at higher frequencies, the signal was a little more shifted. Actually, maybe you might not have noticed that if you didn't have channel coupling on, but that's something it'll do. So you have like your amplitude and phase response. So the amplitude response is where high frequencies like 5 kilohertz, you can't see that anymore. Low frequencies you can still see. So this is kind of what an amplitude response looks like. Let's say the cutoff frequency is around like 0 hertz, it seems. And like up until 0 hertz, the signal is fine. After that, it kind of dies. That's a low pass. Low frequencies pass, high frequencies die. Yeah, and you have other kinds of filters. The Chebyshev filter we gave you is a low pass filter. You have a high pass filter. High pass filters, they block low frequency signals and they allow high frequency signals to pass. Band stop and band gap, those are for certain bands of frequencies. So this is more useful for RF. But if you want, you only want 30 kilohertz signals in your response and nothing less, nothing more. Then you kind of have like a band pass around 30 kilohertz, and then everything else before and after is kind of dead. Let's say you're trying to get rid of mains hum, you might use like a band stop filter at 60 hertz, and then you're gonna let everything go except for the 60 hertz signal. That's kind of what those filters are. So some oscilloscopes, they actually have Bodie plot functionality. So usually you connect it to a waveform gen, or it has an inbuilt waveform gen. You can kind of get a Bodie plot out of it, proper Bodie plot. But let's say you don't have it and you want to do something really quick and dirty. Here's a nifty trick we have, where this is for kind of getting something that looks like a Bodie plot, but it's not really a Bodie plot, but it tells you what the frequency is, or if it's a low pass, high pass. You can get that basic information. So the way we do this is we take our waveform generator, and instead of doing a singular frequency, you see how it kind of goes from these low frequencies and starts going into high frequencies? We're going to sweep across those frequencies, and then we're going to kind of see on we're going to put it through our filter and kind of see on the oscilloscope how the frequency is affected. So yeah, and we also have to zoom out because again, it doesn't like, if we look at this, it's going to kind of go by really fast, and that's not really fun to see. If you want to see a proper, more proper frequency response where you actually see like the entire curvature of it, then you're going to have to zoom out to the point where you can see all the low frequencies on this side and all the high frequencies on this side. So that's like, so on your oscilloscope, that'll be like a full second worth of time. So here's some parameters that you can try. On your waveform gen, look for try to do this in channel 1 because some wave gens don't work on different channels. But if you look, there should be a sweep button on your waveform generator. Press that button, look for the parameters and try to adjust them such that your sweep time is 2 seconds, your start frequency 100 hertz, 10 kilohertz, and your horizontal division is 200 milliseconds.
Yeah. So the sweep button is in this little dialog box right here. Should be the second button in the right column. So you're gonna click that, and then you'll be able to adjust to these parameters.
For eternity and life. Whoa!
So it's a sheet code. So what we'll see is
I'm gonna bring my waveform generator and oscilloscope just so I can play with it a little bit when I'm bored. Just so I can watch these.
So
Bro, I'm pretty sure you have like some 10-hour oscilloscope stuff on YouTube for relaxation.
I put a oscilloscope video.
So what's the waveform
Oscilloscope sweep. ASMR.
Oh, I'm on
is basically triggering at a certain
Oh, studying.
So this one is sweeping across all the frequencies while this one is
Temporary.
as well. So what you can see is that the low frequencies, they're being able to
yeah, horizontally.
after they go through the filter.
Alright.
But then once they get
Zooming in.
high,
Bro, there's no way. Do you know who needs to do that?
Press the button, or press the knob, and now you hit
Steven, make a 10-hour video about oscilloscope sweeps for focusing.
zoom out too much.
For focusing your stuff.
Anyways,
You know, it is possible to connect a computer or whatever.
trying to get this number to like 200.
Well, I don't know about this, but like even wireless.
Something like that.
So,
Yeah. Oh, that's kind of the feeling.
like one
Video
computer.
call.
Yeah.
Like you make it record directly this.
100.
Just film the video and put it in.
No, you put it on a CRT and you make the CRT run. Actually, you would probably burn the CRT.
go for it.
Replacement holes.
There you go.
Also, I think you might have
Instead of regular transistors.
And then
So,
try zooming out.
so we have an idea.
zoom the heck out.
There we go.
We have an idea.
Zoom out.
Over there, it should show you your horizontal division. That's 200.
How much? 200?
So what do you say?
Nice.
Zoom out.
We have an idea.
To 200 milliseconds.
You know this?
Well,
Yeah.
that's microseconds.
We have an idea
Oh,
of
it's
like
micro.
making a 10-hour version.
200 milliseconds. Very
So you
soon.
just like look at it first, focusing and stuff.
It should be
You can't look at it to study.
No, you just put it in front of you, and then like you study on it.
No, that will actually hypnotize.
Okay, zoom the heck out.
Why is there a button to print to a printer?
In case you want backslash yourself. You know?
Demented.
Alright.
Okay, so yeah, we'll just so it seems like most of you guys have it working. If not, we'll get back to this in a second. Okay.
Alrighty. So, looks like you guys are all able to do the poor man's Bodhi plot. So let's get on to our third and final task. We only have a few more minutes, so understandable if you guys need to head out. So let's try to do this real quick. So you guys are given two black box systems. They're really just black tape and red tape, but these are two different type of filters. So your task is, as an engineer, to test it out and see and try to identify what type of filters they are. So similar to the Chebyshev filter, it has an inside and an outside. You can connect it the same way as you did to the Chebyshev filter, and then perform the same sweep of frequencies. And then you should be able to check out which is which. The biggest thing is that once you guys have a solid answer for either of them, you can unwind the tape and see if that works. So, fantastic.
I went to the first one on my list.
Wait, what the hell? It's reading stuff.
I think you need to zoom. Turn it
Like from my
change the
hands.
zoom, and then you should get a better answer. I did change. Just zoom. Let's go way out.
Okay, yeah, cool. That is a high pass. Alright, very nice.
Maybe a bit more
Okay,
energy.
let's try the other one, and that's kind of your exit.
Okay. This does look like a high pass,
Possibly.
right? Like this does look like a high pass.
I think it is a high
Why is
pass,
this
though.
not
Because it's starting at 10.
Alright,
Does that make sense?
Is this a high
This
pass?
is a high pass.
Why would you say it's a high pass?
Isn't it low pass?
Wait.
Wait, no, is it high
No,
pass?
it's like it's so tricky.
Doubting?
Which one is this?
So think about how your sweep of the wave gen is happening.
It's
You're
starting
starting at low
low,
frequencies
so
and then
this
going
is
to
the
high.
start.
Yes.
So it's filtering at the highs. So
Yes.
it needs a low pass.
That's a low. Oh, never mind. I got the name.
That's okay. Does that make sense?
Yeah.
Fantastic.
Basically, this is where.
Okay, low pass.
I love the microsecond features.
Oh my
Start
god.
at low.
That is a, that's certainly a image.
That is an image,
Oh
right?
my.
It's pretty. Wait, do you get the trigger working?
There you go. And then feel free to unwrap the
Oh, it's
trigger.
just nice. Okay.
I've been messing around with the triggers like this stuff. I have no idea what to do now.
Okay,
Okay.
this is
Cool.
What do you think that is?
this
let me
is
look at that
definitely a
one.
high
Let's
pass.
look at that one.
There's another low
Alright,
pass.
it looks like little.
There you
fingers.
go. That's
you
much better.
guys, what's your opinion?
This is a high pass. Is this another low pass?
Yes, correct.
I don't have any.
Switch from low to high. Yeah, low to high.
Okay,
So this must be the low pass. And yeah.
Yeah, right.
This one must be the low pass, right?
Yes.
Cursed with these measurements. It's
Wait,
actually crazy.
Is this was
What's the scope?
We're going to identify what filters what.
That's funny.
Which one's which?
It shouldn't matter.
Yeah, you're showing.
So I was doing the sweep, like it wasn't giving me.
Just grab the edge.
So I was like, well, I'll just try and like sweep it myself.
And then if you
Try it, press it.
No, there's two layers. I'm pretty sure this one.
Why is there a black hand right there?
Yeah, I was wondering. Maybe they wanted them to be literal black boxes. And then,
Are these touching?
No, I've been holding it for fun.
Yes, and it says that the reading link now.
Like it was lightly, it was working before.
Seems like the most simplest hat.
There's a signal. What the heck?
Clean out the wall.
Alrighty. So, just to, yeah, about that, right? Alrighty, just a quick note before you guys leave. I've noted, for those of you that have finished, feel free to keep playing around. Thank you guys so much for coming. Congratulations, you guys found out how to use some of our test equipment. Round of applause. We have plenty of extra slides in these slide presentations that have different features. We cover a few other experiments, resources, things like that. So feel free to scroll through on your own time, and we'll be happy to answer any questions as well. So thank you guys so much for coming. In terms of cleanup, please return all alligator clips to the right buckets, all the cables up to the front, and multimeters, we can help get your room cards back. And make sure all the power supplies and everything is turned off when you're ready. But feel free to keep experimenting as well.
Did you guys just roll the bag?
That is true.
I mean, no more magic smoke.
No more magic smoke.
One side is
Love
for now.
magic smoke.
Keep the doctor away.
I love the smell of burnt resistors.
My electronics formula was blowing up for half days the other day.
Just for fun.
It's for fun. It was fun.
Okay, if you have the card set up, can you get it to light on fire and then blow up?
Really?
Yes.
I would not like to do that.
I like blowing up LEDs because I've done that. Wait, I'm gonna stop the recording.
Oh, I think
Oh, yeah.
Pyrotechnics.
that's the incrimination.
Thank you so much for coming.